All right, ladies and gentlemen, today we are going to start looking at how to solve rational inequalities. So, with rational inequalities, they can vary greatly in the level of difficulty, but this is just going to be an introduction, so we're going to try and keep things realistically on the very basic and introductory level case. We'll get around to some of the more advanced ones later on. So, the process that we're going to be utilizing when we are solving these kinds of inequalities is first we have to make one side of the inequality zero. That's really the only way that this can work. So if there are any terms that are on both sides of the inequality, we're going to need to move it where one side is zero. Since today is just kind of the introductory case, we're going to see that that's already going to be set up when we begin a problem. But as I mentioned, as we increase complexity, that may be something that you need to consider in the future. After we've got one side of the inequality zero, we want to factor, okay? Factor as much as you can everywhere you can, but don't simplify anything just yet. Okay, sometimes that can mess up the process, so we don't want to go and do that. All right. So third, the polynomial side, so the side that all of this stuff has been written on, we need to write it into a single rational expression. Okay, again, for the easy case, like what we're doing today, it's pretty much going to be established for us already. However, in more challenging problems, you may need to add or subtract different rationals together, which is why we had to do all the adding, subtracting stuff before we get to these inequalities. After we do that, we're going to solve, which means set it equal to zero, for the numerator and the denominator separately. These are going to create what are called our critical points. After we have those critical points, we're going to build a number line, and we're going to have to pick some test points in between those critical points. We're going to substitute some arbitrary values back into the original or our greater than or less than zero inequality to see if it creates a true statement or a false statement, and that's going to give us the region of the inequality that is satisfying the particular inequality that we're looking at. Okay, so for today, we're going to take a look at two relatively basic examples. The first one that we're going to take a look at here is x plus 1 over x minus 5, and it's less than or equal to 0. Okay, so looking at the process that we're trying to follow here, first we need to make one side of the inequality 0. Bam, already got it. It's already 0. Second, factor. All right, well, the numerator here is x plus 1. Can't factor that. Denominator, x minus 5. Can't factor that. Okay, that's done. Third, write the polynomial side into a single rational expression. Well, this is the side with polynomials on it, so it's got to be the polynomial side. But it's already written as a single rational expression. Yeah, there's a plus and a minus sign in the numerator and denominator, but it's just one rational expression. So we're good there. So we can go ahead and start working on problem number or step number 4, where we're going to solve for the numerator and denominator separately. I'm going to try and color code it. So I'm going to do the solution for the numerator in red, and the denominator we'll do in this green color. Okay, so we're going to take just x plus 1, and we're going to set that equal to 0. So x plus 1 will equal 0 when x equals negative 1. That's our first critical point. The denominator here is x minus 5. So x minus 5 will equal 0 when x equals positive 5. So those are our two critical points. Okay, like I said, pretty easy examples for today. So we've got our critical points. Now we're going to go and build a number line. Okay, so we're just going to do and kind of do this generic number line looking guy, but I'm going to make it exceptionally long because we are going to need to check some areas here. So the smaller of these two numbers is negative 1, and the larger of these numbers is 5. Okay, so essentially we're dividing the number line into the left region, the middle region, and the right region. Okay, and what I'm going to do next is the part where it says to build a number line and choose some test points. Okay, so what I'm going to do is if these are my critical points, it's really where the graph is changing to be above 0 or below 0. So I'm going to go and pick some numbers. The first number that I'm going to pick has to be less than -1. So I'm just going to pick x equals -2. Okay. The next number that I'm going to test has to be in between -1 and 5. So I'm going to pick 0. If you have an opportunity to pick 0, oh my God, pick 0. It's going to make everything so much easier. Okay. Then my third region, I've got to pick a number that's greater than 5. So a number greater than 5, let's just say 10. Okay. It doesn't really matter which numbers you pick so long as they fit in that particular region. So now what we're going to do is plug this number in to our original inequality and ask, does it make a true statement or a false statement? So if I substitute -2 in for x, I'm going to see that I've got -2 plus 1 over -2 minus 5. And I'm asking, is that really less than or equal to 0? -2 plus 1 is -1. -2 minus 5 is -7. Is -1 over -7 less than or equal to 0? Well, a negative divided by a negative is a positive. So is 1/7 less than 0? No. Okay, so this is false. For the next region, I'm going to go and plug in 0. So I'm going to plug 0 or substitute 0 in for x. So I'm going to test, is 0 plus 1 over 0 minus 5, is that less than or equal to 0? Well, 0 plus 1 is 1. 0 minus 5 is -5, so that makes -1/5. Is -1/5 less than or equal to 0? Yes. Okay, negative numbers are smaller than 0. So this is a true. Thirdly, I'm going to go back and look over here, and I'm going to plug in the number 10. Okay, so I just remember arbitrarily chose 10. Could you have picked 6 or 7 or 8 or 9? Sure, I picked 10. So we're going to go and substitute this 10 in. So 10 plus 1 over 10 minus 5, and we're asking the question, is that less than or equal to 0? Well, 10 plus 1 is 11 over 5. Is that less than or equal to 0? You don't even really need to know what this value is. It's positive. Are positive values less than or equal to 0? No. So here's another false. Okay, so I know that my solution is going to be something that's in between -1 and 5. But last, I need to figure out if it's going to be an open circle or a closed dot. So can it include -1? Well, if I plug -1 in, I'm going to get -1 plus 1 is 0. Doesn't matter what the denominator is. 0 in the numerator divided by something that's non-zero is just 0. So is 0 less than or equal to 0? Yes. So I kind of use this inequality for the numerator and say that's going to be a solid dot. Okay. But if I try and plug in 5 exactly, I'm going to be dividing by 0. I'm not allowed to do that. So the denominator, its critical point or points are always going to be open. And since it's true, it's going to be the region in between -1 and 5. So our solution is going to be written like this. So x equals, we're going to do a hard bracket with -1 because it includes it, and then up to 5, but then it's going to have a soft bracket because it doesn't include 5. Okay, one more example problem. Example 2, we have x squared plus 4x plus 3 over x minus 1 is greater than 0. So I recognize this as a rational because this is a fraction involving polynomials, and an inequality because something is greater than something. So one side of the inequality is already 0. Check. Factor, factor, factor. Ooh, this one I actually can factor. So this is going to get turned into x plus 3 times x plus 1 over x minus 1. Okay, it's still going to be greater than 0. So we could check this to make sure that we did the factorization correct. X times x is x squared. 3x plus another 1x gives us 4x, and 3 times 1 is 3. So everything's been factored, okay? Write the polynomial side into a single rational expression. Well, I only have one kind of division bar here, so that's already been done. So next, I need to solve for the numerator and denominator. So I'll do the same thing I did before. We'll do one of these in green. We'll do this one in blue just to mix it up. So let's find some critical points. So we're going to say that x plus 3 times x plus 1 is equal to 0. So using the zero product property, I'm actually going to get two critical points. I'm going to get x equals -3 and -1. From the denominator, I'm going to find a critical point from solving x minus 1 equals 0, which I'm going to get x equals +1. So I have not one, not two, but three critical points to deal with here. Okay, so again, I'm going to go and make a reasonably long number line. I'm going to put the smallest number, which is -3, on the left, the middle number, -1 in the middle, and the largest number, 1 on the right. Okay, it doesn't particularly matter how they're spaced out. So long as you have them written in the correct order, you should be good. So I'm going to kind of divide these into 4 sections for this problem. And I'm going to pick some test points. Okay, again, it doesn't really matter which ones you pick, but let's go and pick a number that's less than 3, -3. So let's pick, I don't know, -5. In the middle here, let's pick, I don't know, -2. In between -1 and +1, if we can choose 0, definitely pick 0. And then over here, I'm going to say x equals, what's a number bigger than 1? 3. Okay. Again, doesn't really matter which number you're picking, but that's okay. So let's go and substitute in this value of -5. So you can plug it into a calculator. You can plug it into the factored version. You can plug it into the original. I'm going to plug it into the original, but I'm also just going to kind of use big brain time. So if I substitute -5 in for x squared, well, -5 squared is 25. Okay. 4 times -5 is -20, and then +3. All of that's over -5 minus 1 is -6. Is that going to give me a positive number, something that's greater than 0? Well, 25 minus 20 is 5. 5 plus 3 is 8. Is 8 divided by -6 going to give me something that's greater than 0? Nah. So this part, not included in my solution. Next, I'm going to substitute in x equals -2. So if I plug it into the original, -2 squared is going to give me 4. 4 times -2 is minus or -8, and then +3 over -2 minus 1 is -3. Is that going to give me a positive number? 4 minus 8 is -4, plus 3 is -1. Is -1 divided by -3 greater than 0? Well, yeah, because a negative divided by negative is a positive. Positive numbers are greater than 0. So this part is going to be included in my solution. So I'll go ahead and shade a little bit. Next, I need to test x equals 0. So if I plug 0 in, it's real easy. 0 squared, 0. 4 times 0, 0, plus 3. Over 0 minus 1 is -1. So is 3 over -1 greater than 0? Nope, so it's not in the solution. Next, I'm going to go and substitute 3 in. 3 squared is 9. 4 times 3 is 12, and then plus another 3. Over 3 minus 1 is 2. Is that greater than 0? Well, 9 plus 12 is 21, plus 3 is 24. 24 over 2 is a positive number. Is that greater than 0? Yes. So this part is also going to be included in my solution. But I also need to determine if I'm going to be using open circles or closed dots at each one of these critical points. So, because this is just greater than and not greater than or equal to, it's kind of a giveaway that everything's going to be open. Because if x equaled -3, then this would equal 0, and 0 isn't greater than 0. So I'd have to do an open circle. Same thing would happen at -1. If I plugged in -1, I would get 2 times 0 over negative 2. Well, 0 is not greater than 0, so I'd have to use an open circle again. The third critical point that I found was at 1. Well, 1 is from the denominator. The denominator can't ever be equal to 0, so it can't really ever include 1. So all of those are going to end up being open circles. So this is what it looks like on a number line. Translated into interval notation, which is how we want you guys to write it. I'm going to say x is equal to soft bracket, -3 to -1, soft bracket, then union, soft bracket, +1 all the way to the right goes to positive infinity. Okay? So to recap the process, first, you're going to go and make sure that one side of the inequality is 0. For today, all of that's always going to be true. Second, we want to factor everything as much as we can, but don't eliminate anything just yet. Once it's been factored, we want to try and write the polynomial side into a single rational expression. And again, for today, that will already be done. Then you're going to solve the numerator and denominator, which means set them each equal to 0. Those provide you what are called your critical points. Your critical points tell you how to divide up a number line so that you can test the intervals in between them. You can pick pretty much any number you want to plug in to that particular range of values, okay? But it's normally better if you pick numbers that aren't too wackadoodle. So numbers that are pretty close to the numbers that are on your intervals, those critical points, generally speaking, is a better practice than randomly choosing decimals or crazy fractions. Once you have those points, you can then test them to see if it makes a true or a false statement. If it's true, that answer is included. That region is included in your answer. If it's false, that region is not. We can then take the number line, determine whether we should be using open circles or closed dots, depending on the inequality, and whether that critical point came from the numerator or the denominator, and write it out in interval notation.